What I want to do is, so it's a tale of two fuels, and oil and gas. So hopefully by the time I'm done, you will understand why the title was chosen. And so you have to wait till I get to the end for that. I just want to put up a disclaimer. So this is just purely my own opinions and does not anyway represent the views of the U.S. government. Okay, so I thought I'll put up this slide first just to make sure that you guys know exactly where I come from, these two places. So if you do not know the DOE National Laboratory System, there are about 11 of these major labs all around, plus a few small ones. And Brookhaven is right on here in this corner, almost falling into the ocean, on Long Island, which is right here. And Stony Brook is on North Fork. And if you just want to, so JFK is right here. We're about 60 miles from there. And the island is about 120 miles apart from point to point. Okay. So up front, I would like to acknowledge, obviously, the Office of Science and Technology here, State Department for CNR and my bureau, and especially the fact that all the people there are very helpful and have been able to, at least some of them, have been able to interact. It's actually now becoming bigger and bigger. But when I started, there was only like 10 or 12 people in there. There's several of them are here in the audience. So I just want to acknowledge that, and obviously Stas' office. I know there are two people here from National Academies, and I do appreciate for them to be here because we are also involved with them. Up front, I would like to acknowledge a lot of data sources. They have been very, very helpful, actually, in terms of putting this talk together. And one of them that really I'm going to draw upon is the Golden Age of Gas. It's an International Energy Agency's report that came out last year, I believe it's in November. And before that, Beyond Oil and Gas, the Methanol Economy, this is a book that came out, I believe, in 2006 or 2007. And now there's a newer edition of that, written by the Nobel laureate George Olah. He's at University of Southern California and heads the local hydrocarbon research institute. So I just want to acknowledge all these sources. In addition, obviously, there's the MIT report, Shell Energy, and BP Stats, World Energy reports also. So what I'm going to do is walk you down with the very energy basics to start, go into a little bit in oil and gas, and then, because the field is so huge, oil and gas, I'm just going to try to focus on transportation sector, because that's where my case begins in terms of where I think there's a role of gas move into oil markets. And then I'm going to talk about, that's exactly what I'm going to talk, potential of gas to displace oil. And then obviously none of these things are all, these are policy, but what drives, especially this country, is the advanced technology. So I'm going to talk about the role of science and technology in this. Okay, so this is my favorite slide. Question really is, so I'm going to walk you back roughly 1.4 million years ago, when supposedly when the fire was first how to light a fire. And the question is, what's wrong with this cave? Or the picture on the caveman. Well, he's burning something here. And by the time he's done, he's going to put out CO2. He's also going to put out a lot of black carbon the way he's burning it. And there's going to be some ash left. And depending on what he's burning, there could be heavy metals in there. So all these things, I think, is going to be probably addressed in this seminar. So this is my favorite slide. Now, this actually is, I took it off the web, and this actually holds true for most, all the transportation fuel that we use, they are combusted. So there's no question that in terms of energy efficiency, we are so far behind. I think that's a low-hanging fruit. So this is a very, very profound statement from that point of view, that all we do is we light something in a confined space, try to extract as much energy as we can out of this, and then useful energy, but rest goes to heat, waste heat. So that's a big challenge. And that's why I just highlighted here, this process here is combustion. Now, one point I want to make is the way things are looking here. Good thing I'm just bring you back in the present now. If there was an EPA, OSHA at that time, this cave is going to shut down. Okay, so let's go to some serious business. Global energy supply. So I'm going from 2000 to 2030 here in this graph. There are a couple of things to notice. Off the bat, if I just take fossil fuels, coal, oil, natural gas, add it up to here. Look at these three right here, these sections here. You can see already doesn't matter going into 2030 or even going to 2035, huge numbers. They don't let up. I mean, they're a major part of the equation. Doesn't matter how much we want to get rid of them, you can. That's a scenario. And the top part here, above this brown color, is the renewables. Now, if you look at this, yes, they are increasing, but proportionally, these are increasing much faster than these are. And just to give you a little idea, and by the way, out of these renewables, biomass-derived biofuels make a big impact. And then solar obviously is making a dent here, but it's still very, very small. Just look at these numbers here. So 2008, 2005, this is another source, IEA source. I have converted these numbers are in million ton oil equivalent. So if you look at these, 2000 to 35, we have overall projected in energy increase of about 36%. Percent in mix, right here, they go only slightly down from 81% in 2008, right here, to even 235, down to 74%. So we only have renewables, only 26% in this picture. So you see where so what do we do with this? Well, before I go into that, what are the factors this increase in this demand? Well, let's look at the world population 2050. So here are the numbers which are more relevant, I guess. Here 2000 number is 6 billion. And it goes up to 9 billion in 2050, 50% increase right there. And notice here that the non-OECD countries, well, mostly Asia, is where the increase is going to come from. Second, now that's a very worthy cause, and that is, you should look at this graph here from World Energy IEA report. These here are the numbers, people who are without electricity. And if you look at that, the number, since the population is going up, the number decreases somewhat a little bit. In 2008, it's about 1.4 billion, and goes down slightly to 1.2. But still, is a lot of people still in 2035 are still without electricity. I mean, that's a very sobering statistics. Especially in Africa, look at this. This number actually is going up in here, where everywhere else is decreasing. Now, in addition to that, if you look at this graph here, is even energy per capita use. World is right here. Okay, U.S. is all the way up here, about 8,000, and here is mostly Europe. So just take a guess. How much energy is going to be needed where most of the population is now? The whole rest of the world is trying to get up to even to the 4,000 level. It's a factor of about 3 or 4 right there. So, but the thing is, what are you going to say? Don't do it? To all these people, don't come up here? Well, you cannot do that. So therefore, why you see the energy demand is increasing so much over what I graph I just showed you. So with that comes the problem. And that is, this is your CO2 ppm 2011, 392 ppm. And I just put a picture up there. I thought it was cool. You can actually monitor these things from satellite. The red actually shows 385 ppm and the blue is 360 ppm. But if you look at this, under the scenario I just talked about, from 2007 to 2035, these numbers, of course, CO2 number is going all the way up to about, even 2035, we are talking about 42 gigatons of billion metric tons of CO2. So if I take these into account, comes the real challenge, which is the climate challenge. So here is a scenario for the amount of CO2 that we are producing in 2010. And if we don't do anything and just look at the projected increase I just showed you, we are on this trajectory here at 6 degrees Celsius increase in temperatures. We don't want to be on that. Obviously, there's a lot of debate in public. Everybody's aware of that. And what we are trying to get down to is this green line. Can we, by 2035, start decreasing the CO2 output in the atmosphere down to this level, about 22, from 30 now, which is projected to increase about a little over 42 or so, down to this number. But here's the problem. With all the debate for the last 5-6 years is going on, if you look at this, the window is going to close very soon. By 2017. We are locked in. There's nothing we can do anymore to come to this 2 degrees Celsius level. And what I will do is, after I go through my presentation, I'll just show you what are the projections if natural gas is substituted in certain places for oil, and where we can get on this graph. Okay, so here is the problem. Problem is, and by the way, this is the only equation I will show you. I promise that. But it's a very fundamental, and that is any fuel that we burn is a hydrocarbon, has carbon and hydrogen. Those are the energy molecules. Why? When we combust it, remember my caveman picture, combustion, and that is air. We take oxygen out of air, we burn the fuel, and we produce CO2 and water. And when you do that, it comes with a lot of what they call heat of combustion. It comes with a lot of energy, and that's what we want. That's what everybody's after. What I've done in this table actually is, and I'm going to point out here. So these first, gasoline, diesel, they are part of oil, gas, and coal, natural gas and coal. These are all fossil fuels. Bottom, they could be derived from renewables. Now, what are the factors that drive our selection of energy source? What do we burn? Well, whether it's a primary source or it's a secondary source. Example, all these up here are primary source. Primary source means you're going to pretty much dig it out from the, like oil or gas or coal. It's right there, you dig it out, and that's primary source. All these, but I've listed hydrogen. Hydrogen is not a primary source. I can't just dig it out. I have to produce it from somewhere. It's a secondary source. And that has been a problem with the hydrogen, not making it to the hydrogen economy, because where do you get it from? It's always that's the main question. So, but the second point I'm trying to make here is the intensity. Energy intensity per pound. If I took 1 pound of the material, any of these materials, if you look at the fossil fuels, they're all very, very close to 20,000, or gas actually is 24,000, very close. Very highly intense per pound. You can get a lot of energy out. And what that does, well, first thing is, these are renewables like wood, biomass, ethanol from, say, corn, hydrogen. Well, hydrogen is, I told you already where the problem is. Although the best number is right here, 61,000. 1 pound of hydrogen is a lot of hydrogen. You have to get it from somewhere, and that is where the problem with this is. So if I exclude that, problem with the renewables is they are a dilute energy source, means you need more of this to get the same amount of energy compared to fossil fuels. So intensity is a major factor. What's the third factor? So what happens with these is cost. End of the day, it's the cost that matters. And because of the intensity, these things are inexpensive compared to everything else that we're trying to do. But the question then comes is, do these collide? Of course they do, because is the CO2 emissions is a problem then. On this side, I have given you relative emission numbers. I took it from the intergovernmental this climate change paper. The default values is a ton CO2 per terajoules of energy, oil, gas, and coal. because I'm going to focus on that. If you look at the gas, CO2 emissions, no question about that. That is much lower, 80% lower than coal, but 40% lower than oil. So if there's anything that makes sense, it's the gas that makes sense in the fossil fuels. And you know what? There's a reason for that, why this is low. And for that, we actually have a scientific basis, hydrogen to carbon ratio. Methane is primary component of the natural gas. Therefore, it has, for example, is CH4. There are 4 hydrogen per carbon in methane compared to oil, which is about 2. And coal, actually was being nice to coal, actually it's about 0.6. It's less than 1 I put in, but actually more, it's less than 0.6. So therefore, all the problems of emissions that you see associated with these fuels is based on that. And I actually will even go as far as to say that probably if you took everything, even renewables at this point, natural gas does make sense because of the way it burns and the amount of emissions that come out. Okay, so that was my very fundamental energy basics that I want to talk about. Now I'm going to get to oil and gas. Oil. Oil is not simple oil. Oil is not gasoline. Oil is a very complex molecule. Why? You get this oil off the ground, put through a refinery, very sophisticated refinery, and you get all these products out of this 1 barrel of oil. What are these? Gasoline for the cars, jet fuel for the planes, diesel for the trucks and everything else that go with it. If you take all these fuels out of this, fractions that come out, they actually are close to 75 to 82%. And by the way, you can, depending upon, for example, European refineries are more geared towards making diesel, fraction more, compared to the US, which makes more gasoline because of our needs. Because we use more gasoline than with diesel, European is opposite. So if you look at the transportation sector in this oil, of course, about transportation fuels are the principal components of this. Of course, this goes to heating, home heating, and so on and so forth, the rest of the stuff. So this is my very involved picture here, U.S. energy consumption. Petroleum, natural gas, coal, renewables, and nuclear. This is our mix right here. Petroleum is 37%. What is the end use for these? Transportation, industry, residential, commercial, electric power. Notice something, electric power is huge. And most of actually, a lot of natural gas goes into that. Coal is primary, 92% goes into that. But I'm going to actually talk about right here, the transportation sector, because I think that's where one of the issues is that need to be addressed if we're going to have gas make into the transportation sector. So, but look at the numbers. So it's 71%. What about natural gas? It's only 3% right now going into the transportation sector. Okay, so I'm going to move on to natural gas. This is where all the fun has started for the last few years. Global supplies, about 808 TCM. And by the time this number put up, I think it has already increased because we are finding gas everywhere. Everybody's finding gas everywhere. About 250 years worth. That's the estimate right now. It will last for a long time. Compared to coal, which is about over 100 years, and oil, they keep finding oil too, but right now say about 50 years. So, question is, will natural gas replace oil? And in what shape or form? Can it provide the energy security for the US, obviously, because this slide, it's a very interesting slide. So this slide, I'm going to just go back here. This scale here represents right here how many TCF. I get a little confused sometimes because most of the EIA, which is the US reporting agency, we still talk about TCF, trillion cubic feet, whereas everybody else talks about BCM. All the reports are billion cubic meters. So our TCM, trillion cubic meters, more metric units. But anyways, relative numbers, interesting picture. This is a picture about 2 years ago, 2010 picture. Before that, just imagine if we took the top, only leave the blues. If I just leave the blues, that's the conventional gas. We are, US, very poor in conventional gas compared to rest. So are everybody else. But all of a sudden, if you add on this top, nice colors here, this red and green, this is the tight gas and coal bed methane, which is CBM, and the shale gas. Together is called unconventional gas. If you add those up on these, on top of this, what you have a totally different picture at this point. In fact, although you have to admit, this is Russia, former Soviet Union, FSU, Middle East, they still come out pretty good, even with these put together. Although Canada and US, I mean, their numbers are pretty high at this point in terms of the supply. Now, I have shown these numbers on this, but in terms of production, it's the US right at home that is leading the revolution in this case. In the last couple of years, it has come to a point where we are going to become net exporter of natural gas from a lot of net importers a couple of years ago. So this is the what I want to call is a supply plentiful gas, and what has that done to the price compared to oil? This is a really interesting graph. Just to give you an idea, natural gas and oil prices, you got to multiply the price of natural gas million BTU by a factor of 6 to make them equal energy equivalent. Okay? But after that is all cheap gas. Therefore, look at what has happened since 1994 to 2012. Normally, if you look at this, except for these two spikes here, where the natural gas prices spiked up because there was a shortage, normally, historically, it tracks pretty well about minus 20% range or so in this range here. Look what has happened since, especially after 2006. Look at the price. In fact, this price here is today's price, which is less than $2 a million BTU. And that puts natural gas to about $12 a million BTU equivalent. Sorry, no, $12 a barrel oil equivalent. Huge difference in oil and gas prices. So there's no question then, all of a sudden, which U.S. business and so business everywhere else, what are they here for? To make money, and also to come with innovative way to exploit these resources. And that's exactly what they're trying to do, that if we do have such a inexpensive gas in this country or anywhere, everywhere else, why not exploit it and to do that? So therefore, those two, the supply and the cost, is really opening up a lot of opportunities in this area. Now, I'm going to spend a little bit of time on this. So what has happened, here's the production numbers. And U.S., by the way, was almost is number one and number two producer last year next to Russia in terms of the amount of gas produced. So this here is you see is unconventional gas. This is the conventional gas production for 2010 numbers. It's about 3.3 TCM, trillion cubic meters. And out of that, this number is about 16% or so is the unconventional gas, which was almost nothing 5 years ago. And it's mostly in the US. So we are basically driving this whole thing with the gas revolution. Also, something that people do not appreciate, when you increase the gas production, they're associated what they call natural gas liquids, which are a little higher hydrocarbon than methane, ethane, propane, butane, and so on and so forth. They go back into the gasoline pool, also used. So there are associated natural gas liquids that you also get with the natural gas. So that's added benefits. Two more things, I will talk about that because that is not addressed, and that is the flared gas, and the renewable gas also now is a part of the equation, although this is not showing up right now, but going to the future, it should. But the thing is, so we have a lot of gas. So what's going to happen? There's always a mismatch. So you have gas here. People are here. For example, Asia is starving for gas. Japan is starving for gas because of post-Fukushima. So what is going to happen? We need to move this gas where the people are. So we have a couple of, obviously, traditionally, pipelines are the way to go. We have still, pipelines are always there internally, especially on land, but even undersea, everybody's doing that. But LNG now is becoming actually more prominent in this area for transport. So I will actually, next slide, I'll spend a little bit on LNG. LNG stands for liquefied natural gas. It is gas, but it's liquefied. And just a very simple reason so that we can transport easily. Okay, so once it goes to the intended destination, what are the end use for the natural gas? Well, most of it is going for making power. So you can back out of coal, which is already happening, and you can use natural gas. Industrial, other processes, steel making, and so on and so forth. But for the transportation sector that I'm going to talk about, you can also, that's called natural gas vehicles. You can also use natural gas as a compressed natural gas, which is CNG vehicles, or LNG vehicles also that are coming, also very, very small market, but, and then liquid fuels. There's another option. Gas is something that you can actually convert into liquid fuels. And that gives you a little better flexibility in terms of moving the gas around to the markets, because gas as a liquid fuel, you can actually make fungible hydrocarbons. You can make diesel out of that. You can make gasoline out of that. And the car doesn't know where it came from. It's exactly the same molecules, so you can substitute. So there are fungible hydrocarbons you can make from gas. LPG supplement, I don't want to spend time in that, but this is actually really exploding in Asia, some of the liquid that are coming out of this. But I think these two are the new markets that are coming up. One is for the diesel substitute, natural gas, and also as a fuel extender. And I'm going to spend time on this. So for the transport purpose, we have liquid natural gas shrinks volume by 600 times if you liquefy, if you cool it down to minus 162 degrees Celsius. It goes down by 600 times. Means the same volume, you can now have a lot of gas come in. Therefore, it makes it easier to transport. But it comes at a cost because you need an infrastructure. Liquefaction terminal. So wherever you are on the export side, you will need a liquefaction terminal. And then once you have that, you have liquefied it, you will need a dedicated LNG tanker. That's going to carry, these are funny looking tankers with these domes. For a reason. They cannot use your regular liquid tanker. These are dedicated tankers for LNG. And regasification, once it arrives at the port, at the receiving port, you need a regasification terminal so that they can then evaporize and make it again to natural gas, the gas. Now, problem is right here. Cost for $1 billion per billion cubic centimeters is what the cost is to do this. LNG tankers, typically about 33 million gallons it can carry LNG. Cost 0.2 to 0.3 billion. Regasification terminal at the receiving end, 1 billion for the 10 BCM. Not small numbers, but people are still making these investments to move gas because this is still cheaper than trying to build pipelines, or you do not have an option of building a pipeline. So therefore, projecting into from now into 2035, I think it's almost going to be 1-to-1 projections from LNG versus pipeline, how the gas is going to be moved. And the numbers are about 620 BCM gas will be moved via these two options. Okay, so let me now focus a little bit on the transport sector. We know we run cars on gasoline, but there are other parts of the world, I mean very few in the US, but other parts of the world, we have in fact globally about 12 million CNG run vehicles. These are compressed natural gas. And what you do, here's a tank. It's a high pressure tank because I told you before, problem of the gas is that you have to really get a small volume for it to have a meaningful in terms of going distance. So in this case, if you pressurize this tank at fairly high pressure to 3,000 PSI, and that's what this tank is in a car, then you may be able to go still not the same distance, but at least meaningful distance. The reason you don't want to go higher than this is because then the cost is very prohibitive, number one. Number two is it's becoming more dangerous to carry is around 7,000 psi tanks. And there's another problem in the U.S. U.S. we have long distances people travel. Other countries, there's smaller distances. They can actually, for example, Pakistan, about 2 million vehicles actually are run on CNG. So, but 2035 projections from the gas scenario, that's the IEA report where they call it a gas scenario, where they say if the gas happens this, this, and this, where we go with this. So then there's a gas scenario from IEA, projecting numbers of about 70 million from 12 to 70. Percent of global fleet be still very small, 4.4%, but the natural gas usage is also very small, it's about only 3.4% of the total, because the projected at this point in 2035, natural gas is going to be about 5.1 TCM, global number. But if we did that, net oil reduction potential is not small, it's 2.3 million barrels per day oil we can back out by using compressed natural gas for road transport. And because the numbers I showed you with the CO2 reduction potential here is also follows that to about 25%. So not a bad thing to do. But what is the constraint in these things? Problem is it needs a gas distribution structure so you can have these high pressure filling stations all around just like you have gas stations so people can do that. So what is our second option? I think that is where I'm going with this. Can we convert gas into liquids and then use that? Well, here's natural gas. This black box is what you do is thermal process that produces a bunch of gases here. And depending upon what you want, you can actually make everything that I have listed here, all these fuels. Now, what is this? Ethanol, everybody knows. In the US, we make ethanol from corn through fermentation process. But you can also make ethanol from natural gas. There's another thing coming on the horizon, which to compete with ethanol is butanol, because it has more higher energy density. DuPont and some other companies, in fact, have a commercial plan coming up pretty soon online. And the second one here, I did discuss that is your drop-in replacement fuels, fungible hydrocarbons. It's a known process. You can actually process the natural gas into these liquid fuels. And last one actually, which is not a liquid, but you can also get hydrogen out of that. And in fact, just to give you an idea, most of the hydrogen comes from natural gas at this point, about 75% in the whole world. So I am going to talk a little bit about this, methanol and dimethyl ether. The reason for that is because these things are already showing up in the Asian markets as a substitute for fuels. So if we did that, turn gas into a liquid, any of these, see, oil has a liquid infrastructure. It doesn't need any new gas stations to do that. You can have the existing liquid fuel structure. You can actually use those. Second, that allows us then very smooth transition from the oil, from the gas into the oil markets. So let me focus actually on methanol and dimethyl ether as a transportation fuels. Methanol is a very interesting molecule actually as a fuel. You can directly use it as fuels. Everybody knows Indy 500, they have used methanol for a long time as a race. Race cars use fuels all the time because it's more efficient. So it's nothing new about that. Dimethyl ether actually is quite interesting, derived from methanol, or you can directly make from methanol. Dimethyl ether has so methanol actually you can do two things. One is used as a neat fuel, 100, don't need any gasoline, or you can use just like we do with ethanol right now, and that is M15, 15% methanol in gasoline. DME actually can be a direct diesel substitute with a minor modification into the diesel engine trucks. You can run the whole truck on DME, not on diesel. You can totally back out of the diesel. So it's a very good replacement diesel substitute. And which is not part of my talk, but this is driving another thing here is that countries like China, Iran, and everybody else are using cooking fuel, blending with the propane, LPG, with a DME 20% blend. You can also make gasoline directly out of methanol, just like you have same gasoline that you put in your cars, a replacement for petroleum gasoline. Car would not know the difference where it came from. And this process, by the way, from methanol to gasoline process, is called the MTG process, the methanol to gasoline process that was developed by Mobil Oil Company, and it was run in New Zealand, a commercial plant for a long time in the 1980s. So all these technology that I'm talking about, they do exist. So what is the market then for the liquid fuels here? U.S. market, renewable corn ethanol, we have a 10% blending. We can go only 15%. There's a blending wall. You can go more than that. Global markets is where the real action is. Then Brazil, we actually, U.S. and Brazil are the only ones who have embraced ethanol. Because for Brazil it makes sense. They have sugar, and all the waste goes to make ethanol. Perfect thing to do, integrated. So we actually account for about 87% of the global ethanol market for consumption. Okay, what about the rest of the world? Well, they are not doing anything except burning gasoline and diesel. So if what happens, now I'm going to give you a scenario. What happens if we blend methanol with gasoline at 15%? There's no problem there. Or dimethyl ether, substitute for diesel, or mixing with LPG. Well, that I'm not going to talk about too much. That's cooking. But here is the transportation sector right here. So this technology status for these things, mixing, blending, is going on right now in commercial trials in China and Iran. And here is what is the numbers are, to give you the numbers. So what I have done, these numbers, is I have converted these numbers, these are 2011 numbers, and I have converted these numbers to billion barrels of oil equivalent per day. So you could actually look at these numbers, say, okay, this much oil we can back out. These are all normalized numbers. Total global production of methanol. The reason I put this number here together is because methanol, DME is derived from methanol, so I have put the number together, both of these. Global production for 2011, 560,000 barrels of oil equivalent per day. China, this number actually is their, not the production, but actually the consumption number, 55,000, very small number because they are only trying one province this year. This is 15% volume gasoline in China, and DME number is 32,000 in China. 2020, China is developing the infrastructure to go for DME to 300,000, about 10 times in about 10 years. Iran, surprisingly, is also, because I don't think you know this or not, they export oil, but they don't have enough refining capacity, so they actually need 80,000 barrels per day oil coming back to them refined gasoline. So therefore, their idea is that if they could actually use methanol, they could back out of that 30,000 right here. This is going on right now in Iran to look at the trials in this. Now, for China, this number here is only in one province, and it represents only about 77% of the gasoline pool in China. If you look at the numbers for China, this year is about 8 to 9 million barrels per day numbers for the consumption of gasoline. If you do that, this number actually explodes to about 1.35 million barrels per day for oil you can back out in China. So the numbers are actually fairly staggering for these. So what I did is just to give you a flavor, if I took all the gasoline in 2035 projections, gasoline and diesel, remember both of these come out of oil, so 27 million barrels per day, diesel 36.5 million. If I took these numbers and I say, okay, instead of purely burning these now, why don't I have a 15% methylene gasoline M15? I back out, I need 4 million barrels per day. Remember, this number, global number, includes the US number, which already uses ethanol. I took that out. The net global demand for methanol could be 2.7 million per day, oil equivalent. DME replaces diesel at 10%, 3.7 million per day. If I took these two numbers, total potential oil displacement is about 6.4 million barrels per day. It's not a small number, huge number. And I'm only talking about just right now, only 15%. The last slide I showed you actually had a number that China planned to produce cars to run on totally 100% methanol, as well as 80% methanol. If those numbers go up, the numbers obviously go by a factor of 5. So I just want to give you a little bit of a flavor for where the gas can actually start making, backing out of oil, and gas starts going as a liquid. Now, source of gas for GTL. Where this gas will come from, what the magnitude is. Not that much. This in billion cubic centimeters. In 2010, it was only a partly 10 BCM. Remember that we used in 2010 3.1 trillion cubic meters of gas, and only 10 was for gas to liquids. In 2015, there's 2 plants coming online for methanol and also for hydrocarbons made from natural gas in Nigeria and Qatar, and therefore the number is going up to only to 25 BCM, not a big deal. But there are other sources I pointed out to you. There's a flared gas, which is about 134 BCM per year, has no use, it's just being flared, and I'll show you in the next slide. It's really an issue. Renewable gas, we produce in landfills about 45 BCM per year. If we increased our gas usage only by 15%, and that doesn't take too many of increase because we have 250 years of projected supply, we can actually only need about 495 BCM. And if we did that, the total of these come out to about 675 BCM of natural gas. That equals about 14 million barrels per day of methanol, and that translates into equivalent oil displacement potential of 7. The reason is because methanol has only half the energy of oil, so therefore you divide by 2, 7 million barrels per day oil you can back out. Not a small number. So I just want, this is something very important. This is what I was talking about, the flared gas. This is totally flared, had no use, mostly in Nigeria. Nigeria is one of the biggest countries that flares it. It's about 5% of total gas usage, this number, and puts out about 400 metric tons of CO2, or 2% of the total CO2 global emission just comes from here. So the reason for that is there are policy issues. They have limited access to the international local gas markets, lack of financing for infrastructure, and undeveloped regulatory framework, somewhere where maybe the U.S. can help to move it forward. So there is a World Bank has an initiative called Global Gas Flaring Reduction GGFR initiative, and that initiative is exactly aimed to see what can be done to this gas, utilized not just flare it and put the CO2 in the atmosphere. And interesting is that alone would be 1.4 million per day potential right here. And that number was included in the last slide I showed you. If you ever have time, just say GGFR on the internet and watch this YouTube. It has a really cool stuff where the flaring is going on all around the world. It's a really cool YouTube video. So since I'm in a building where cook stove is a big deal, I thought I'll throw this. Cook stove and black carbon. This is a NASA image here of the black carbon. And what is our approach in this building is we are going for better cook stoves, and we have made a big inroads in this area trying to reduce carbon in the parts of the world where they are producing all this black carbon because they are just using stoves open. Just what I showed you what caveman was doing, there's no different. It's exactly what's going on. So what happens? Transition to cleaner fuels like DME derived from natural gas may be the next leapfrog technology. And this thing actually, I took it from the web because there was a presentation from Mongolia in the recent conference, and China and Mongolia actually are looking into this, especially in Mongolia. Mongolia, some of their places are like terrible in terms of air quality. So there's a big push in the next 5 years to replace going into DME as a fuel to address those issues. So I thought I'd at least put that out. I think I'm almost time. So let me summarize then. So I'm going to pose a question. The question was, is gas a bridge fuel going from the carbon economy into whatever non-carbon economy we are aiming for, or the low-carbon economy that you're looking at all these these words coming out, low carbon economy or whatever you want to call it. Well, how do we get from here to there? There's no question gas is a good bridge, okay? Because it's a cheap source of supply, but also less CO2 reductions at the same time. Gas conversion to liquid fuels allows an infrastructure that's compatible already with oil. Gas should be really viewed, as I said before, as I emphasized, as a clean extender of oil fuel, not as a competition, but actually just a clean extender. And next thing is very important, because what I have told you so far, we still have a way to go in terms of the commercial processes to develop these liquid fuels to get to a point where they start competing equally head-to-head with LNG and other technologies. And we are almost there, but it's about here. We need to come up to here. So therefore, no question that science and technology play a crucial role in process development, and there are a lot of good things coming on those lines. I don't have time to go through that, but I think we'll get there. And if there's anything, Caribbean and Pacific Islands, they are terrible at this point. All they do is they get this diesel from tankers and they just keep on burning. That's how they're doing. This could be a good, these here, target for diesel replacement with methanol and DME in those islands as going forward. So this is the slide I have. So the gas scenario, the IEA, whatever I have talked about, it puts it about not here where we are trying to aim at, but they call it 3.5-degree scenario, not 2. By doing what I just showed you with the gas, natural gas going into different sectors of power, oil, and so on and so forth. I only cover the transport sector, but if you start substituting, that's how you can get to that. Remember, we want to get over here. We still got a way to go, but I think the liquid fuels probably can get you a little bit more here, because that was not covered in the gas scenario that the IEA report. So that's what I have just covered. That's something. The reason I covered is because, just to give you an idea, in the liquid fuel production of natural gas was when I started actually at Brookhaven. That was my first project that I started when developing technologies for that. Okay, so this is not a bad scenario for considering what we have to deal with in terms of population and other issues. So I'm going to end with this, the remarks by the President on energy. You know what? All of the above energy strategy is the same strategy to go. There is nothing else. Can be too radical, totally going to biofuels, because there is no way forward for that. So therefore, I think I firmly believe this is the way to go, all inclusive. And with that, you already read that so many times, but I just wanted to point out that producing more oil and gas here in America, I mean, that's the way to go. So with that, I'm going to end, and thank you very much for your patience and listening. Yes?
You mentioned Iran producing large amounts of methanol. Mm-hmm. I assume they need some kind of a catalyst to do
yes.
that? And do you know whether they import a catalyst or they make it?
Okay, so Iran is in a really good position because I believe in about 2 or 3 years ago, they now have the largest methanol production plant at 10,000 tons per day already existence in Iran. So they have a lot of methanol. So it is no surprise they decide to go with that. Now, the technology that they use to make methanol, these are known technologies, and there are three companies pretty much control it. One is Lurgi, Germany. Second one is actually Mitsubishi. But before that, ICI, which is now Davy in UK, they had pretty much all the technology to make methanol. There are other companies, and in terms of the production, the major player is Methanex. They are based in British Columbia, Canada, and they are the one who control actually most of the methanol markets in the globally. But in terms of production, yes, there are more technologies coming up, but Iran technology, if I understand, is one of those three.
Yeah, I'm sure you know why I'm asking in terms of sanctions and what hurts. This may be a target.
Well, they're producing for themselves. That's all I can say. I'm only talking purely from the scientific point of view. Sanction, I don't think I want to talk about because I don't know about sanctions to say anything about that. Yes.
So, Devinder, part of the economic appeal of natural gas and the natural gas derivatives is the price discrepancy on a per BTU basis between petroleum and natural gas.
Yes.
But the very large discrepancy that you showed is peculiar to the Western Hemisphere market. And if we consider natural gas to be three markets, one in Europe and another in Asia,
yes.
The one that most closely tracks the price of oil is the Asian market for gas, where gas is heavily used as a transportation fuel.
Mm-hmm.
So what is your perspective on the amount of natural gas that could be used for transportation before we would start seeing similar linkages in our own gas markets?
Very good question. First thing, let me give you a little picture. When I said in the U.S., right here we have less than $2 million BTU gas, cheap like hell. I mean, I can't get any cheaper. Maybe, I don't know. But you look at the European market, they are paying close to 8 to 10. Japan, rest of Asia, they are more 12 to 14, that range. So there's a discrepancy. There are no questions about a factor of 7 from one end of the spectrum to the other one. So the question start coming up is, where would you do this? There is a price sensitivity analysis done, and it compares the price of methanol with gasoline. And of course, feedstock is a component of that. So at $4 a million BTU, you are about $1.30 a gallon, equivalent to gas. At $8 a million BTU, you're about $2. So when it gets $2, remember, then you have to add on the cost like everything else, then it starts going up where it was. So if you're asking whether they should do that in Asia to make, depends how they get the gas there. But one possibility what we have been saying is, okay, so where the gas is, convert that right there into liquid, and then transport like in a regular tanker like you do, and transport that. It is not that you transport LNG to Pakistan, for example, and then start making methanol. That's not going to make any sense because it's expensive. By the time it's delivered, the price is $12. So that will not make sense. So only thing is, within the country, supposedly Pakistan, for example, they have found a lot of in the northern regions gas fields. You can help develop that their own, not with imported gas. It's a captive gas. They could utilize right there. And one thing I have always said, if you find gas here and you can use the gas here, don't do anything with it. Just use it. Don't transport it. Don't do anything. But for them, the country is starved for energy. That makes sense. But from here, in this country, for example, right now what we have, maybe the best option is to also start making. And in fact, that just to give you an idea, 2 months ago, Methanex actually announced that they owned a plant in Chile that came online about 12 years ago. They have dismantled that because Argentina shut the gas off. So now what they're going to do is they are taking the entire plant, this 5,000 tons per day plant, and they bring it to Louisiana to make methanol in Louisiana that was shut down 5 years ago. So anyways, so the problem is, yes, there has to be going forward. What I have put together essentially is purely scientific reasoning. Now, going forward, what we need to do is a little bit different, addressing the markets. Does that answer your question or no?
A little bit.
Okay.
I'm just curious. We've seen other non-petroleum fuels track the price of essentially what the market will bear, which is whatever the cost of the petroleum-derived fuel
Yes.
is.
Yes.
And so I'm wondering if you've done the assessment or have any anecdotal evidence to describe what that would be in the U.S. for
Okay.
the local natural gas market to start tracking the price of petroleum as well.
Okay, so here, right now, I don't know how long they're going to stay below 2. That's my problem. Answering that question, say $4 million BTU probably is more realistic to sustain the surplus that we have, because otherwise the producer will stop shutting their wells. As you know, they're capping them now because they don't want to sell for $1.90. They don't make any money. So if we take $4 or even $5, I think it's more realistic. At $5, if you first convert to energy equivalent, that's 30. Okay, energy equivalent. Now, if you take that number, give the conversion number, I think it comes to about, I'll say $40 a barrel equivalent, which still is not bad compared with the oil is. But historically what has happened is that as soon as OPEC and other countries who make money out of oil, they see something coming that is in competition, thus oil prices start dropping, so that's how the track is. It's a little bit more complex than, but you're asking for parity. I think it's about $40 a barrel. At this point will make sense. You can actually produce that equivalent from gas.
Thanks.
It's on?
Yes.
Okay. Darren Tui, I'm a Jefferson Science Fellow as well, and working in EAP-EP, the Economic Policy Office. And last week I was at an Institutes of Medicine. They held a fracking meeting
Yes.
on health impacts assessments. And someone from the Environmental Defense Fund spoke about the global warming impact of natural gas extraction if there's fugitive emissions. And the interesting result, which is not out of line with what I'd seen before, but I want to throw it out there and have you comment on it, was that anything larger than about 1.5% fugitive emission of methane takes away the entire benefit of natural gas. So essentially, compared to coal, it makes it equal to burning coal. Actually, it may have been burning oil, but it was one or the other. There's a big difference there. But in any case, do you know about any of those studies, and what are your thoughts about the ability to produce natural gas, not just in the U.S., but also worldwide, from all these plays that people are finding at the level below 1.5% fugitive emissions?
Okay, so let me. I'm going to answer that question. If the history is any example, all the questions that are coming up with fracking, remember, it's come down to technology, okay? And that's the only time when there's a problem that is identified. For example, in this case, is fracking, extracting natural gas and associated emissions. That is where the science and technology will address this issue that has come to it right up the top at this point. So if you're asking me to give you some harder numbers, I mean, you have seen the Cornell study back and forth last year, and you know all the numbers there. I have seen those numbers too. All I can see is since this problem now is, well, not a problem, but this is a challenge that has actually now is out in the scientific community. It's open. I am firm believer that in the next year or two, you will start seeing technologies with recommendations coming up that can actually then reduce to a level where it will be making sense just like conventional gas. That's all I can say at this point. But having said that, I do want to point out, in fact, Joe here is sitting here, he's in our bureau. Their job is, they have a whole initiative, global initiative for unconventional gas, just to make sure that since U.S. is the leader, that we are learning from the lesson that we are learning from everything that you just described, that when we go and help other countries develop this resource, that we are advising them on the technologies so they don't themselves go around and start digging something out and it makes it worse. So their job is just that. In fact, that's what they do. They hold seminars and everything else just to educate. So the Bureau ENR is very much involved in that, just for that reason, what you just described. China is the next. If you believe their numbers, now they're obviously saying that they have more unconventional gas than the U.S. does. Fine, whatever. These numbers are always going back and forth. But Bureau is engaged with China for that reason, because they want to make sure that everything is done properly. Otherwise, somebody does something bad because they don't know the technology, don't have the know-how. They blow up something, everybody gets a bad name. So that's exactly the reason the Bureau is so much involved, and that is why the Bureau's importance actually is there. And I just hope that is the reason for the Bureau to be there in existence.
So just to follow up, when you were going through the slides and putting this together, did you get a sense that we know what the fugitive emission numbers are? Do we have a good handle on that scientifically now?
I do have them. I don't have them with me.
Okay.
I did look at those numbers. Here's the problem. You have seen the last year's controversy, right? The back and forth between the two Cornell groups,
right.
university.
Right.
So, yeah, it depends upon how you calculate. I mean, you know that what was going on in those two papers, back and forth. Again, as I said, because of that controversy, it is out in the open to the scientific community as a challenge. I'm a very firm believer in science and technology. So therefore, you talk to me a year from now, I think you will see a totally different numbers. Because, hey, it is all driven by curiosity, science and technology, and that's a challenge at this point. So I'm pretty sure we'll have something.
Okay, thanks.
I mean, you have those papers anyways. I mean, I don't have to give you those papers, but I do have those back and forth commentary going on between the two Cornell University groups. This is the first time I ever saw there are two groups from the same university actually banging heads. I have no idea how the Cornell University president had to say about that, because one will lose. Anyways.
Oh, for sure, it's not the first time at a university. You cited an MIT study. I think they debate their issues as well. So I'm Gilbert Brown. I'm a Foster Fellow, not to be confused with other kinds of fellows, but to be blended, I suppose. And I work in nuclear, which you already mentioned in a sort of an offhanded way. And so I don't want to talk about nuclear, but I do want to talk about energy. And I really liked your slide because the first 20 minutes of your presentation is actually my presentation as well, and many of us who talk about energy and the role of a source that we know about fits into energy. So I wanted to focus you not on transportation, but on the use of gas for electricity. And in a related way, the use of electricity for transportation. Because if we don't look at this holistically, you're banging your nail into the wood, other people are banging their nails into the same wood, right? And if you don't look at it that way, I think we're going to miss good opportunities. For example, using gas to make electricity, because coal is what's used almost 100% to make electricity. So I'm really interested in gas as a bridge away from coal, and nuclear as well, because these are ways to get, I don't say off of coal, and we can't, because your slides say 3/4 of our energy, and most of that is coal, is fossil fuel. So my question is, can you comment about gas for electricity, and then that comment about what happens to gas when everybody starts using it? For sure, it's not going to be $2. For sure.
Okay, so let me answer your first question. I actually had a slide on. Say you're going to electric cars. Okay, that means I think that's what you're referring to. You need more power, but you're going to run your car on electric then. And for the delta that you need extra power, you could generate from natural gas-fired plants. there's no question what is happening right now. Look in the power sector. I mean, our bureau, one of the offices looks at the power sector. That's what they're looking at. I didn't have the time to look in the power sector. Look at the numbers there. I mean, power sector is much bigger, pie-wise, than the other sector. Okay, but what is happening is with the natural gas the way it is, and with all the regulations coming in the U.S., for example, EPA regulations for the coal, unless you're grandfathered or whatever the reasons are, I think you're going to start seeing some switch. Okay, Ohio is one of the examples that has just done that, but again, it's a problem is that existing infrastructure is the way you want to go after, because unless there's a reason. The reason is because there's I just showed you this, there's so much extra that we're going to still build. If you can just address that, it's much easier to do that than trying to have an existing infrastructure. Hey, you start burning coal, you start burning natural gas. Unless for them themselves there's a reason to do that. And they will go it. Remember, business is business. It's not a magic bullet.
Gas is not magic.
Yeah, I'm just saying that it's a business. I mean, if they realize that going to gas is cheaper, they will do it. But just saying, getting up in the morning one day, says, hey, stop all the coal-fired plants, let's go to gas. It ain't going to happen, because who's going to pay for it? For the conversion. So, but that's when they develop their own business models. If they find out if I convert now, and if you're going to project those prices for the next 10 years, that where is going to sustain, that's how you make the decision. So what I'm saying is two things. One, for the extra power we need to say, if we go to electric vehicles, not use oil in the cars, that delta could be built based on natural gas, no question. But any other substitution, that will be based on case-by-case basis. They have to decide.
There is a concern about blowing up these LNG tankers in New York Harbor or something?
No, I mean, think about it. I mean, those things are fairly nicely built. That's what they look like, And in fact, something's very cute about that. You know how they run these things? These LNG tankers? So when it's a liquid, but so it's cold, it's minus 162 while it's in the voyage. So what happens is that during the way they are shaped like that is because on purpose there's a slight that there's a relief valve. So about 1.5% of the gas actually is relieved. What that does, it actually keeps the rest of the gas cool. And what they do is I didn't know before I found out, they actually capture that gas, and they have actually a dual fuel with diesel, with bunker fuel, whatever they use, to actually they burn that gas that's coming out of there for the journey. So it's a pretty cool thing what they're doing. But in terms of safety, I mean, these days, I don't think the safety regulations are so stringent. Again, I'm not a safety inspector myself, but I'm pretty sure with the cryogenic technologies that are out there, something like that happening, unless a Somali pirate takes over or something and they're sitting on it doing nothing, I don't know. I'm just making this up, but but otherwise, under normal conditions, I don't think you have a safety issues.